Welcome back. Today we are talking about galaxies that broke taxonomy. JWST, the James Webb Space Telescope, discovered a handful of tiny, weird galaxies in the early universe that do not fit any known category. Scientists are calling them platypus galaxies.
Platypus galaxies. So you found cosmic creatures that are half bird, half mammal, and lay eggs in space?
Not exactly, but the analogy is apt. Just like the platypus defied biological classification when European scientists first encountered it, these galaxies defy our current models of galaxy formation. We will look at what JWST actually observed, why astronomers are confused, and whether this is a missing link in cosmic evolution or just another case of humans naming things after Australian animals.
So, mystery galaxies, confused scientists, and the possibility your entire classification system is wrong. Humans. Really?
Let us start with what JWST found. A team led by Haojing Yan at the University of Missouri was combing through archival data from JWST's deep extragalactic surveys. They identified a small sample of 9 galaxies that exhibited a previously unseen combination of features. These objects are extremely distant, meaning we are seeing them as they existed in the very early universe, roughly a few hundred million years after the Big Bang.
9 galaxies. Out of billions. And humans are already naming a new category? Bold assumption. Zero evidence. Classic.
Well, 9 is a small sample, yes, but the features are striking. These galaxies are incredibly compact and tiny. Even with JWST's impressive resolving power, which can show us fine detail at enormous distances, these objects appear as tiny dots. That is unusual because most early galaxies we have found so far are either extended and messy or clearly associated with massive black holes.
So they are small, far away, and your telescope cannot figure out what they are doing. Sounds like my opinion of Earth's political systems.
The confusion comes from the spectroscopic data. When you split the light from these galaxies into a spectrum, you can identify emission lines that tell you what elements are present and how the object is shining. For these 9 galaxies, the spectra are ambiguous. They do not look like typical star-forming galaxies, but they also do not match the signature of quasars, which are supermassive black holes actively feeding on gas.
Wait, you are saying they shine like nothing you have seen before, but you still don't know if it is stars or a black hole. That is like looking at a light bulb and not knowing if it runs on electricity or tiny hamsters.
That is actually a decent analogy. The spectra fit multiple interpretations. One possibility is that these are compact star-forming galaxies with unusual properties. The other is that they host small but actively growing black holes that are obscured or behaving differently than the quasars we know. The team cannot rule out either scenario with the current low-resolution spectra.
So your universe is stranger than you think, and your data is too blurry to tell the difference. Maybe invest in better glasses next time.
JWST is already the best infrared telescope humanity has ever built. The issue is not the quality of the instrument, but the nature of the targets. These galaxies are so faint and distant that even JWST needs long integration times to collect enough light. The spectra the team has analyzed so far come from survey programs that were designed to map large areas of sky, not to zoom in on individual faint objects. Follow-up observations with higher resolution spectrographs are planned.
All right. Explain to me like I'm a confused earthling who just learned what a galaxy is. What is so weird about these platypus galaxies, feature by feature?
First, their size. These galaxies are extraordinarily compact. Most galaxies in the early universe that we have identified fall into two broad groups: extended irregular star-forming galaxies with chaotic structures, or bright point-like quasars where a central supermassive black hole dominates the light. The platypus galaxies are neither. They are tiny, smaller than the star-forming regions we typically see, but not bright enough in the way quasars are.
So, they are too small to be normal baby galaxies and too dim to be black hole disco balls. Got it. Continue.
Second, their spectral features. When you look at star-forming galaxies, you see strong emission lines from ionized hydrogen, oxygen, and other elements heated by young massive stars. When you look at quasars, you see broad emission lines and a continuum spectrum shaped by the hot accretion disk around the black hole. The platypus galaxies show emission lines, but the pattern is ambiguous. Some lines are present, others are weak or absent, in ways that do not cleanly match either category.
So the chemical fingerprint is smudged, like someone tried to forge a cosmic ID card.
That is one way to put it. Third, their number density and environment. These 9 objects were found in deep survey fields that cover relatively small patches of sky. If this is a real population and not just a statistical fluke, it suggests there could be many more such galaxies out there. That would have implications for models of how galaxies assembled in the first billion years after the Big Bang.
Or it could be 9 cosmic typos. Ever think of that?
That is why the research is preliminary. The team presented these findings at the 247th meeting of the American Astronomical Society in January 2025. The results are available as a preprint on Archive, which means they have not yet completed formal peer review for publication in a journal. The scientists themselves are cautious. They are saying, "We found something odd. We need more data."
So, what are the actual hypotheses? Star babies or baby black holes?
Hypothesis 1. These are ultra-compact star-forming galaxies. If that is true, it would mean JWST is seeing a population of galaxies that form stars in an extremely dense and efficient way, unlike anything in the local universe today. That could tell us something important about the conditions in the early universe, such as the density and temperature of gas clouds, the rate of star formation, and the feedback processes that regulate growth.
So, tiny star factories running at maximum efficiency. Why is that surprising?
Because our simulations of galaxy formation do not predict this kind of extreme compactness so early. Most models suggest that early galaxies should be messy and extended because the universe was still dynamically young. Gas had not yet settled into stable disks. Mergers were frequent. Dense compact galaxies usually appear later in cosmic history, after billions of years of evolution and merging.
So the universe ignored your theory. Again. Humans, often wrong, never in doubt.
Hypothesis 2. These galaxies host small, actively growing black holes. Not the billion solar mass monsters we see in bright quasars, but intermediate mass black holes, maybe thousands to hundreds of thousands of solar masses. If the black holes are embedded in dense gas or oriented at certain angles, their emission could be partially obscured, which might explain the unusual spectra.
So, maybe there is a black hole inside, but it is wearing a cosmic hoodie, and you cannot see its face clearly.
That is surprisingly accurate. Some quasars are known to be obscured by thick clouds of dust and gas. The challenge is that the spectra of these platypus galaxies do not show the strong X-ray emission or broad lines we usually associate with even obscured black holes. That makes this scenario harder to confirm without additional high-resolution observations.
Okay, what does the wider scientific community say? Are other astronomers nodding along or rolling their eyes?
The reaction has been cautiously interested. Multiple news outlets and science communication channels have covered the findings. The consensus is that the result is intriguing, but needs verification. The sample size is small, the spectra are low resolution, and the interpretation is ambiguous. These are exactly the conditions where scientists say, let us wait for more data before rewriting textbooks.
So the scientific method is working as intended. Boring, but responsible.
Exactly. This is actually how frontier science works. You find an anomaly, you publish preliminary results. Other teams try to reproduce the observation or find similar objects. Then you refine your models. The fact that this is generating discussion is a sign that it touches on important open questions about galaxy formation.
Fine. But why the platypus? Why not the cosmic penguin or the space aardvark? What is the marketing strategy here?
Haojing Yan, the lead researcher, chose the platypus analogy because the platypus is famous for breaking taxonomic rules. When European scientists first encountered a platypus specimen in the late 1700s, they thought it was a hoax. It has a duck bill, lays eggs like a reptile, has venom like a snake, but also has fur and nurses its young like a mammal. It took decades and genetic analysis to understand that the platypus is a monotreme, a unique branch of the mammalian family tree.
So it is an animal that evolution cobbled together from spare parts. Sounds like these galaxies.
Exactly. Yan said that just like the platypus shares genetic features with birds, reptiles, and mammals, these galaxies show features that overlap between different known categories. The imaging shows extreme compactness. The spectra show emission lines. The brightness suggests active processes, but none of it cleanly fits the existing boxes of star-forming galaxy or quasar.
All right, let us talk context. Why is JWST finding weird stuff now? Did Hubble just miss all of this?
JWST has a few key advantages over Hubble. First, it observes in the infrared, not primarily in visible light. The early universe is receding from us so fast due to cosmic expansion that the light from distant galaxies is redshifted into the infrared. Hubble could see some of this, but JWST is optimized for it. Second, JWST has a much larger mirror, 6.5 meters compared to Hubble's 2.4 meters. That means better sensitivity and resolution. JWST can detect fainter objects and see finer details in galaxies billions of light years away.
So, Hubble was driving with foggy glasses, and JWST put on night vision goggles with a magnifying lens. Got it.
Third, JWST's instruments include sensitive spectrographs that can measure the redshifts and chemical compositions of extremely faint targets. That combination of imaging and spectroscopy is what allowed Jan's team to identify these platypus galaxies in archival data. They were probably in Hubble images too, but Hubble could not characterize them clearly.
So, JWST is basically humanity's attempt to upgrade from dial-up internet to fiber optic when it comes to looking at baby galaxies. Impressive. For humans.
Now, let us address a deeper question. If these galaxies turn out to be a new population, what does that mean for our understanding of cosmic history? The first billion years after the Big Bang are critical. This is when the first stars ignited, the first black holes formed, and the universe transitioned from a dark neutral fog to a transparent ionized state. That process is called reionization. We do not yet know exactly which objects provided the ultraviolet radiation that reionized the universe. Was it mostly stars in small galaxies, or was it quasars and black holes?
So, you are saying the universe went through puberty and you are still not sure what triggered it. Awkward.
If the platypus galaxies are compact star-forming systems, they could represent a missing population that contributed significantly to reionization. If they host intermediate mass black holes, They could be the seeds of the supermassive black holes we see in the centers of galaxies today. Either way, understanding this population helps fill gaps in the timeline.
Or they could be neither, and you will have to invent a third box. Have you considered that your categories are just human constructs and the universe does not care?
That is actually a valid philosophical point. Categories in science are tools for organizing observations, not fundamental truths. When observations do not fit, we either refine the categories or invent new ones. That is how progress works. The discovery of quasars in the 1960s forced astronomers to accept that supermassive black holes exist. The discovery of gamma ray bursts led to new models of stellar death. If platypus galaxies are real, they will push us to refine our models of early galaxy evolution.
So, science is just a series of humans confidently drawing boxes and then erasing them when reality does not cooperate. I respect the honesty.
Now, let us talk about what happens next. The team needs higher resolution spectra. JWST has instruments like the Near Infrared Spectrograph, or NIR spec, that can deliver detailed spectra of individual faint targets. With better data, astronomers can measure emission line ratios more precisely, detect weaker features, and distinguish between star formation and black hole activity more confidently.
So, the plan is point the fancy space telescope at the weird dots for longer and hope the data stops being ambiguous.
Essentially, yes. They also need to search for more examples. 9 objects is suggestive but not statistically robust. If hundreds of similar galaxies turn up in other survey fields, that strengthens the case that this is a real population. If no more appear, it could indicate the original 9 are outliers or misidentified.
So, either you find more platypuses and declare victory, or you admit those 9 were cosmic flukes and move on. Haha, classic science.
Another angle is multi-wavelength follow-up. JWST observes in the infrared, but combining that with X-ray data from telescopes like Chandra or radio data from ALMA, the Atacama Large Millimeter Array, could reveal hidden black holes or unusual star formation activity. Different wavelengths probe different physical processes. Infrared shows stars and warm dust. X-rays reveal hot gas and black hole activity. Radio traces cold molecular gas, and sometimes jets from black holes.
So you need multiple telescopes to triangulate reality, because one telescope alone cannot be trusted. Sounds expensive and complicated. Also sounds like the only way to do science properly.
Exactly. Astronomy is increasingly a multi-messenger, multi-wavelength field. One dataset gives you a hint. Combining datasets gives you the full picture. That is especially true for ambiguous objects like these platypus galaxies.
All right, speculation time. If these galaxies are real, what is the wildest but scientifically plausible explanation for what they are?
Wildest but plausible. One idea is that they represent a transitional phase. Maybe they started as compact star-forming regions and are in the process of growing a central black hole. Or the reverse. Maybe they are black holes that recently shut off, and the remaining starlight is what we see. Another possibility is that they are the result of galaxy collisions or mergers in the early universe. When two small galaxies slam together, the gas can compress into a very dense region that forms stars rapidly. That could produce a compact, bright object that does not look like a typical galaxy.
So, cosmic car crashes creating Franken galaxies. I like that theory.
There is also the chance that the compactness is an illusion caused by orientation or by foreground obscuration. If a larger galaxy is oriented edge-on or wrapped in dense dust clouds, it might appear smaller than it really is. But the team thinks that's unlikely given the number of objects, and their similar properties.
Or, controversial idea. Your models of galaxy formation are incomplete, and the early universe was weirder than your simulations predict. Ever consider that?
That is not controversial at all. That is the default assumption in cosmology. Our simulations are only as good as the physics we put into them. We know there are uncertainties in how stars form, how black holes grow, how feedback from supernovae and black holes affects gas, and how dark matter influences structure. Every time we get new observations from a more powerful telescope, we find surprises. That is why we build the telescopes.
So, you are saying humanity builds billion-dollar machines specifically to prove itself wrong. Respect.
That is science. Let us wrap this up. JWST discovered 9 small compact galaxies in the distant universe that do not fit existing categories. They are too compact to be normal star-forming galaxies, and too ambiguous spectrally to be clear quasars. Scientists are calling them Platypus Galaxies because, like the biological platypus, they defy simple classification. The discovery is preliminary. The sample is small. The spectra are low resolution. Follow-up observations are needed to confirm whether this is a new population or a statistical fluke.
Translation. Humans found 9 weird dots, gave them a cute animal name, and now have to spend years figuring out if those dots mean anything or if they just got excited over cosmic noise.
If they are real, platypus galaxies could teach us about the earliest stages of galaxy and black hole formation. If they are an instrumental artifact or misidentification, they will teach us about the limits of our current data. Either way, we learn.
You know what? That is actually a decent philosophy. Fail forward. Learn either way. Humans are annoying, but occasionally wise.
Want to stay updated on cosmic mysteries, strange discoveries, and the uncomfortable moments when the universe does not fit into neat categories? Subscribe to our channel. Science meets skepticism in every episode.
Hit like if you think naming galaxies after animals is the best part of astronomy. Subscribe if you want to know when scientists finally admit the universe is weirder than their textbooks.
And until next time, stay curious.
And remember, if your galaxy does not fit the classification chart, just call it a platypus and wait for more data. Works every time.